To do these notes, you should at best print out this handout that's in topics, and I also make available probably in the assignment, and then fill it in by writing down. If you can't print, or if it's hard for you to print, you can always follow along and you can write down on a sheet of paper, whatever works best for you. If we were doing this in a classroom, I would have handed this out and you would be filling it in as we go along. So go ahead and try 1, 2, 3, and 4. And pause the video if you want. I'm going to put up answers. All right, here are the answers. This here is the definition of capacitance. How many coulombs of charge you get on a capacitor divided by how many volts of potential difference it takes to create those coulombs of charge. Remember what that Q means. Here it is rewritten so it's easier to do the algebra, and then here is the way engineers would write it and the way I learned it. We understand that the V really means not a potential difference at a point, but or not a potential at a point, but an electric potential difference between 2 points. Right? For any given capacitor, we can change the charge by changing the voltage. We can hook it up to a different battery and get a different voltage, which creates a different charge. But the C is constant for a given capacitor, the same way that the R is constant for a given resistor, and the V, technically delta V, is constant for a given battery. All right, let's continue. Let's say you start with an empty capacitor and a resistor and you connect it in series to a battery. Go ahead and sketch that circuit. And here's what it should look like. It should look like that. Okay, and then here's the way we talk about the capacitor. Even though we know negative electrons are moving, when we talk about current, current means the direction positive charges are moving. So our model is that positive charge does what under the top plate and does what from the bottom plate. So outside it looks like so-and-sos are doing something. So we say there is a blank through the capacitor. That may not be completely clear, but I'll put up the answers. In our model, we say that positive charge is landing on or entering on the top plate and then leaving from the bottom plate. So one charge will enter the top plate and then push away a different charge from the bottom plate. But from the outside, since the capacitor is just a box, it looks like the positive charges are just going through the capacitor. So we say there's a current through the capacitor, even though really there's not a current through the capacitor. By the way, if you're interested in electrical engineering, eventually you'll learn that the same thing happens with a battery. The charges don't actually flow through the battery. They actually land on the negative plate in our model, and then different charges leave the top plate, the top terminal. But that's not part of our course in the AP Physics. All right, go ahead and read these questions, number 6, and try to answer them. And here's what I was getting at with number 6. If the charge on the top plate is plus 3 coulombs, the charge on the bottom plate will always be the same absolute value but negative, so negative 3 coulombs. So the net charge on a capacitor is always 0. So when we say charge on a capacitor, the Q on a capacitor, it's not its net charge, but instead it's the charge on the positive plate. Some teachers will say it's the absolute value of the charge on either plate. That's fine. That's no problem with that. Okay. Go ahead and sketch this circuit, a 12-volt battery connected to a 2-farad capacitor and a 3-ohm resistor. And what I mean by that is in series. It doesn't say that here, but that means in series. Go ahead and sketch that circuit, and you should get something that looks like this. And as always, you want to pause the video at any time if you need to catch up or think about what you're looking at. Okay, for that circuit, you should be able to answer these questions. When you start at t equals 0, what are these values? And then a short time later, look what's given here. What's given is that the charge on the top plate is 12 coulombs. Then after a long time, the circuit reaches its final state, fill in what these would be. Okay, here are the answers. What's given when you start is that the charge on the capacitor is 0. It's a neutral capacitor, and that means, since Q equals CV, that the voltage across the capacitor is also 0. We know that the voltage on the battery is 12, so that means the entire 12 volts has to be across the resistor since the voltage on the capacitor is 0. Since you have a voltage of 12 on the resistor and a resistance of 3, you get a current of 4. A short time later, the charge on the top plate is given as 12, so that means immediately on this next one, you would write 12 coulombs here because that's what's given. As soon as you knew that, since you know the capacitance, you use that to find the 6 volts on the capacitor. That would be the next step. Since the total voltage along the circuit elements has to be 12, because that's the voltage on the battery and they're in series, the voltage on the resistor is now calculated to be 6. And since you know the resistance is 3, you can use those two numbers to find out that the current at this point is 2 amps. Then finally, after a long time, the circuit reaches its final state. So what would be given first here, what would be given is this, that as time progresses, the charge on the capacitor builds up. Those positives are landing on the top plate and leaving the bottom plate. When does that end? When does the charge stop? When does the charge that's going like this, and it looks like it's going through, when does that stop? Well, it stops when the voltage on the capacitor reaches the same voltage as the battery, and you have that balance, what I call a push of war, so that neither one is winning, and at that point the current stops and becomes 0. So you know at that point this voltage is 12. That would be the first thing you would know. Using the capacitance, you could then figure out that the charge on the capacitor is 24. Since this voltage is 12, you could have also gone straight to this, that the current must be 0 because of that push of war being an equal 12 volts on the battery, 12 volts on the capacitor. And since the current through the resistor is 0, since V equals IR, the voltage on the resistor has to be 0. All right, next we do something that I mentioned in the first video. If you now disconnect the capacitor from the final circuit that we had before, so it's fully at that voltage it had before, and we disconnect it. It's got charge on the plates, and we disconnect it without losing that charge. And you connect it in series with a switch to a 3 ohm resistor. There's no battery in this circuit, so go ahead and sketch the circuit. Here's what it should look like. Now look at the givens here. It's given in the problem that this resistance is 3 ohms. But this part, all of this over here, comes from the previous circuit. We disconnect the capacitor and it does not lose its charge. The charge stays on it. We're not going to short circuit it and make that charge equalize and become 0 on each plate. So it still retains the 24 coulombs. Since it was given that the capacitance was C equals 2 farads, from these two numbers here, you immediately know that the voltage has to be 12. Using this information, everything in here, you can answer the next questions. So the next question is C. You close the switch. Explain what happens. That means tell me what happens in the circuit. We're using circuit terms. And will this continue forever like an ideal battery? Okay. What happens is a current goes this way. You have positives here, and they will go this way, so you have a current through the capacitor and through the resistor. Can that happen forever as if you had an ideal battery? And the answer is no. Next, try to answer the questions for the quantities in these 3 situations. When you first close the switch, sometime later when this is given, the charge on the capacitor, and then after a long time. All right, here are the answers. What's given in the first part is that we have a charge on the capacitor of 24 coulombs, and that immediately leads us to know we have 12 volts on the capacitor. And since the capacitor is directly connected to the resistor with nothing else, the resistor also has 12 volts, and you can use V equals IR to find this current is 4 amps. Sometime later, what's given is that the charge on the capacitor is 18 coulombs. So that's the thing you would write down first. Charge is 18 coulombs. Then you use the equation for capacitance to find this voltage. The next thing you would do is, since it's directly connected to a resistor in series or in parallel with it, you now have that the voltage on the resistor is 9 volts. And since V equals IR, you can find the current is 3 amps. And finally, after a long time, the circuit reaches its final state, and you can see how this is different from a battery. Everything's zero. All of the charge has left the top plate of the capacitor, moved through the resistor, and gone to the bottom plate, so now both plates are at 0, so we say Q equals 0, therefore V equals 0. Since V on the capacitor is 0, V on the resistor is 0, and since V on the resistor is 0, the current through the resistor is 0. The next topic is to develop a formula for the capacitance of a parallel plate capacitor. Now, there are different ways to make capacitors. There are different shapes. You can use a solid ball inside a spherical shell. You can use a cylinder inside a cylindrical shell. There are lots of different shapes. The only shape we're really going to worry about today is the most common shape, the parallel plate capacitor. Now, it seems clear that this should have different capacitances depending on the dimensions, that if we made the plates bigger, we would expect the capacitance to be what? We would expect the capacitance to be bigger, and that's pretty obvious. What's not as obvious is if we move the plates farther apart, if we make this interplate distance bigger, then the capacitance gets smaller. That's not as obvious. So I don't expect you to do this next part on your own. Find an expression for the capacitance of the above parallel plates in terms of these dimensions and constants. You're not going to do that on your own. I'm just going to show you the little proof. You really don't have to worry about the proof for the AP test, but you should understand the implications of the result. So here's the proof and the result. We'll talk our way through this situation. There's a lot in here that's helpful for you to know, but you don't have to be able to do this proof for my test or for the AP test. If we make these two plates have opposite charges, it creates an electric field between them. So that's the physics of the situation, and you should know that. Here is the definition of capacitance. You should also remember this from before, from the chapter on Gauss's law, that if we have a uniform field like this, then the potential difference is just that constant E times the distance between the plates. It comes from the definition of electric potential difference, which comes from the definition of how much work is done. And the amount of work that would be done would be the electric force times distance, but then we divide out the charge and we get the electric field times distance. That's the potential difference. So you've seen this before. All right, and our method, remember our goal, we want capacitance as a function of the dimensions, the interplate distance D and the area of a plate A. So our method is to write this and then replace the delta V with something that has a Q in it, so the Q's cancel, and we get an expression that just has the dimensions, the area and the distance between the plates. Here is the proof of it, and I'm going to go very fast with this because you really don't have to know this. You come back and look at it yourself if you're curious. But we start with this. We really start with this idea, and then we say, oh, we want to replace the delta V. It must depend on Q. If there's more Q, there's more voltage difference. So let's replace that. And to replace it, we're going to start with Gauss's law. There's Gauss's law, remember that from before. And we solve for E, but the voltage difference between the plates is ED, as we said before. So the voltage difference is this expression here times D. So there's that expression times D. And then finally, you take the expression for capacitance, you replace the delta V with what we just found here, you get this mess. But then the Q over Q makes a 1, and when the smoke clears, you get this. And this is what we wanted. And remember, this is for parallel plates only, because way back here, right here, this here was only for parallel plates. That's not generally true. And up here, we use the idea of constant field, which we can use for any capacitor when we do this proof. But here, this is true only for parallel plates with that create a uniform field. This is by far the most important one you need to know. The most important. There are formulas for the capacitance of different shapes, but this by far is the most important one, and this one is on the AP equation sheet, more or less. And here's what I mean by more or less. This letter has appeared here. This is actually what's on the equation sheet for the AP test. What is that letter doing there? Well, that's a constant for different materials that are between the plates. If what's between the plates is a vacuum, this constant is 1, so it disappears. If what's between the plates is air, this constant is very, very close to 1. It's like 1.000 something. So we treat it as 1. It's like 1 to 3 significant digits or more, so it disappears for air. And those are the introductory types of capacitors you need to know, the ones with air or a vacuum in between the plates. So we don't write this constant because it's just equal to 1. However, I'm just planting a seed here. We'll come back to this later. For now, you don't have to know it. For today's homework, you don't have to know it. This constant, notice it's not actually a capital K because it's the same size as this. It's actually a Greek letter. It's not a lowercase a because these two are the same height. This is the Greek letter kappa, and it's called the dielectric constant. And if you put different materials between the plates, this number here is larger than 1. It's different for different materials, similar to the coefficient of friction. We don't have to know about it today. So there, I made it disappear. This is what you have to know about today, although that kappa does show up on the equation sheet. You just use that kappa. You need to know what it is if there's something between the plates other than air or vacuum. Now I want you to look at this for a second just to see what it's telling you. It tells you that the capacitance, if you have a parallel plate capacitor and you want to make the capacitance bigger, what are the two things you could do? You could increase the area of the plates, or you could decrease the distance between them. You could push them closer together. There are physical reasons for that second one, but we won't deal with that today. The next topic is to look at capacitors in parallel. Just as with resistors, when we looked at resistors in series and parallel and discussed formulas for them and what had to be the same for them, what could be different for them, whether bigger, smaller, that sort of thing. We do the same thing with capacitors. So first write the equation for capacitors again, and then draw 3 capacitors in parallel and try to answer these questions. Which quantity must be the same for all 3? Explain why, and which quantities can be different for them. All right, and then here are the answers to those. There are 3 capacitors in parallel. Notice parallel means they're connected across the top, and also their bottoms are connected. One wire comes out the top, so we can connect that to a battery, and one wire comes out the bottom, we can connect that to a battery. Since they're in parallel, the only thing that has to be the same for all 3 is the potential difference, delta V. Explain why. All you have to say at this level is that they're in parallel. What could be different for them? Clearly, we could buy 3 different types of capacitors, 3 different capacitors with different numbers of farads. So C, capacitance, could be different for them. And also the charge could be different. Since they all have the same voltage, but they have different capacitances, that means they could have different charges. Charge could come in here, say 10 coulombs could come in here, and 3 coulombs could go here, 2 coulombs could go there, and 5 coulombs could go there. Right? And notice what I just did. I took that 10 coulombs coming in and I broke it up into 2, 3, and 5 coulombs, and 2 plus 3 plus 5 equals 10. No charge is destroyed or created, so you have to account for it all. So the charge on the 3 together has to equal the amount of charge that came in. And likewise, 2 coulombs would leave this one, 3 coulombs would leave that one, and 5 from that one, so a total of 10 coulombs would leave them. And that brings us to what comes next. We want to talk about the total capacitance of this arrangement. And so you think of them being in a box and you can't see inside the box. You put a certain number of coulombs of charge into the box, the same number comes out. You can measure the delta V across the box. So in terms of those letters, how would you define the total capacitance? Well, here's how you would define it. You would define the total capacitance as the charge that went into the box divided by the total potential difference across the box. All right, so now we'll use that above, the analysis above to find the equivalent capacitance of these 3 different capacitors when they're in parallel. And the key to this, you don't have to know the proof. But in looking at the proof, it's not difficult. It's not a difficult proof. And in looking through it, you do learn some things about capacitors that you do have to know. And also the proof, to prove these things, the proof helps you zero in on 2 ideas. What has to be the same for these circuit elements and what must be different for them. And then the other idea is which of the quantities, electrical quantities, can be expressed as a sum, which is necessarily a sum. So now we'll look at that proof and you'll see what I mean. All right, so there's our circuit. Q comes in and is split into Q1, Q2, and Q3. then those leave the capacitor's bottom plates and become Q again. Each capacitor is different, C1, C2, C3, but the potential difference across them is all the same because they're in parallel. So here's how you do these proofs. The same thing works for resistors. 2 steps. You start with a necessary sum. You figure out which one of these 3 quantities must be a sum. And notice it will never be C. It can't be C because those are individually given. It's one of the electrical quantities, Q or delta V. So which one must be a sum? In this case, when capacitors are in parallel, the charge must be a sum. The total charge going in has to equal the sum of the 3 individual charges. So you always start with a sum, then you do a replacement. Since Q equals C delta V, you replace every one of these. Q1 is replaced with C1 delta V, etc. Over here, the total charge that went in is replaced with C total, the total capacitance of the group times delta V. And if you don't understand why, look at the previous page. All right, now why did I just write delta V instead of delta V1, delta V2, delta V3, and delta V total? Why did I do that? Because they're in parallel. They're all the same. The delta V1 equals delta V2, etc. So there's no reason to use a subscript. The next step, look at these. What would you do to simplify this? Well, you divide them all by delta V and you get this. You get what we want. A formula for the total capacitance of capacitors in parallel, and that's equal to the sum of the individual capacitances. Notice that's like resistors in series. These are capacitors in parallel, but the formula is like resistors in series. It's the opposite. All right, and then we'll finish by looking at capacitors in series. Draw 3 capacitors in series. Which quantity must be the same? Explain why. Which quantities can be different? Same as before, and then try to do the proof. If you really want a challenge, try to do that all yourself. Now we'll go through the answers. And I'll go a little faster this time because you've seen the patterns. Right, there's 3 capacitors in series. Now, this is something where even if you don't learn the proof, this question C is very important because it's something that might not occur to most people immediately. The Q on all 3 has to be the same. Clearly, the capacitance doesn't have to be the same. You could buy 3 different capacitors. The voltages don't have to be the same. You could connect this to a 10-volt battery and have 2 volts, 3 volts, and 5 volts. Right? They could be different. But what does have to be the same is the Q. And here's one way to think of it. If you have, let's say, 5 coulombs go into the top plate here, that means 5 left the bottom plate. So this will be Q equals plus 5, Q equals negative 5. And if those 5 coulombs left the bottom plate, where do they have to go? They have nowhere else to go but the top plate of the next one. So this winds up with a charge of 5, which means this has a charge of negative 5. So this has a charge of 5, and this has a charge of negative 5. So the thing that has to be the same for all 3 is the Q when they're in series. That's a very important point to remember because it's not something that you immediately realize the way you immediately realize all the other points about what's the same or different. Here's my explanation why. The idea of being trapped. If the charge leaves the bottom plate of one, it has nowhere else to go but the top plate of the next. So each capacitor will have the same Q. Right? Obviously, these answers are obvious, so we'll skip ahead to this. All right, here they are. Each capacitor has the same Q, which is the charge on the top plate. The voltage, delta V, is across all of them. Each one has an individual delta V, like that, and each one has an individual capacitance. So just as before, we start with a necessary sum, and you can see since they're in series, that has to be the voltages. Total voltage is the sum of the individuals. Then you use Q equals C delta V. You use that to replace all the delta V's, and you get fractions like this. We use the same Q for all of them for obvious reasons, which means we can divide that out. So we divide by Q, and we get that familiar reciprocal formula we've seen before. And notice this is like resistors in parallel, which means the rules for capacitors in series and parallel are the exact reverse of the rules for resistors. And if you just remember that, then it becomes easy to understand them. Okay? One last thing though, we'll go back over one more thing. If you put capacitors in parallel, notice the formula you get. This means that the total capacitance is always more than any one of them. The total capacitance is always larger than the smallest one, or than the largest capacitor. And you can think of that, look what you're doing. By arranging them this way, it's like you're making the plate wider. You're taking that cue and you're spreading it out over 3 plates instead of just one. So it's like making the area of the plates wider without changing the interplate distance. So if you go back to the formula we figured out before, it's like you're making the A bigger by putting the capacitors in parallel. And if you put them in series, look what that does. You're putting a charge on the top plate, and if you think of this as a box, there's the top plate, and then there's all this junk in between, and here's the bottom plate. So it's like you're stretching the top plate farther away from the bottom plate. So it's not exactly equivalent, but it can help you remember it to realize what you're doing is it's like pulling the plates apart and making this distance bigger, and that would therefore make the capacitance smaller.